All right, chapter 10, think and rank. Problem 35. All right, so when you have these vectors here that you're breaking up into components from an official math point of view, and so you've got, so if velocity is like this, there's a certain horizontal component and vertical component. Now, the official math way is beyond the scope of what this course is about, but for those few people out there, you would use trig. And so the horizontal component would be the magnitude, so the 10 meters per second or 20 meters per second, times this cosine of the angle will get you the horizontal component, and then times the sine of the angle will get you the vertical component. Now, without that, let's make the assumption that the angles that they have here are all the same. And so, sorry, that the angles that are drawn here are accurate. So the 37-degree angle actually is a 37-degree angle and so forth. Also making the assumption that the length of the vectors is drawn accurately, that all the 10 meter per seconds are the same length and the 20 meter per second is twice as long. So given that, the vertical components is simple enough to do just looking at it, that if you look at just look at how high up they go. B is the highest, then C, then A, then D. Another way of looking at it is that the smaller the angle, the more horizontal that force or that velocity is, and the bigger the angle, the more vertical it is. So if you're comparing AC and D, that's simple enough as for the horizontal, the lower the angle, the more horizontal it is. So that would be DAC. And the bigger the angle, the more vertical it is. And so that would be CAD. B is the tricky one for the for the horizontal. And you can just, take a pencil or something like that. Just use your finger. How far down across your finger does it go horizontally? And then compare that to the others. And so looking at that, it goes to almost my knuckle there. I know you can't see it, but trust me. And D, which is the most horizontal, the 10 meters per second doesn't go as far. So B has the biggest horizontal and vertical component. The acceleration doesn't care about the velocity. The acceleration cares about the forces involved. And so since the only force acting on is the force due to gravity, if it's being thrown, since at the peak, it stops briefly, but it doesn't care because the force of gravity is the dominant force there. And the force due to gravity causes acceleration due to gravity, which is the same for all of them. For 36, this is a conservation of energy problem, at least for parts A, B, and C. If they all tossed off the edge of a cliff at the same speed at different angles, assume that they actually leave the hand at the same height, then the potential energy relative to the ground is the same. Potential energy involved here would be the gravitational potential energy. Since they're dealing close to a planet, the lowercase g is relatively constant, and so we're dealing with a formula of mgh. The potential energy depends upon the mass, the acceleration due to gravity, and the height. Mass and acceleration due to gravity are the same, so that just leaves the height as the key thing here. They start at the same height, same potential energy. Kinetic energy of the balls when tossed, if they're tossed at the same speed, and that's all this, it says a ball, so let's assume it's the same mass every time, then kinetic energy is the same. Kinetic energy doesn't care about velocity, it cares about speed. So speed's the same, mass is the same, kinetic energy is the same. When they hit the ground, energy is conserved here because once it's in the air, the force is the force due to gravity. It's a conservative force, and therefore, once it leaves the hand, force of gravity is the only force, and so therefore the energy is conserved. So they start out with the same energy, they end with the same energy. It's all potential at that point relative to the ground, and therefore we have, and therefore the kinetic energy is the same. Time of flight is different. The one that's tossed up in the air does take longer to get to the ground, and so time greatest would be B, then A, then C. 37. So for 37, we have dashed lines of the orbits. So in terms of orbital speed, basically the thing orbits because of gravitational pull. And you might have to look at your notes for this one. So plugging into F equals ma, you have big G, mass 1, mass 2 over that orbital radius squared is equal to the mass of the object that's orbiting times the speed squared over r. Then that the speed squared over r, that's the centripetal acceleration because it's traveling in a circle. So if you reduce that, we get an r. one of the masses drops out, the mass of the object that's orbiting drops out, and you're left with just the mass of the planet, and then you cancel out an r, and so what you end up with is that the speed is equal to the square root of g, mass of the big G, mass of the planet over the orbital radius. The essence here is that the speed gets slower the farther you are away. Another way of looking at that, if I threw an object, remember it has to fall at basically the rate at which the planet is curving, and so the farther out it goes, it doesn't have to travel as fast. Similar to if you have an orbital radius, as it gets closer to, so it shows up in 38, as you get closer to the sun, for instance, it speeds up a little bit as it whips around, and then it slows down and it speeds up. So the closer you are, the faster it's going. So the orbital speeds will be ranked from A, B, then C. Now the time to orbit the Earth, we'll simplify it down to Kepler's third law, that the orbital radius cubed over the period squared is a constant for all things orbiting the same central object. He did it specifically for the sun. But it's r cubed over t squared. So as r, and r cubed is proportional to t squared. So as r gets bigger, t gets bigger. And so the time to orbit the Earth will be CBA. 38, yeah, well, and also back on 37, it's traveling faster at A, and it doesn't have to travel far to travel, so of course the time is going to be the least there. 38, position of satellites in elliptical orbit are indicated, and so gravitational force, you're ranking various things. So gravitational force is the greatest when they're the closest, because we're dealing with two constant masses. So A, B, C, D, gravitational force. And then that would also be the ranking for G. In other words, part G, acceleration, because acceleration is dependent upon the force. That would be magnitude of acceleration. Now recognize part of that acceleration is centripetal acceleration, because it's changing directions, and part of it is change in speed, or known as tangential acceleration. Rank the speeds. It does get faster as it gets closer to it. If I throw a ball in the air, it slows down as it goes away from the planet, and speeds up as it comes closer. And so speed will have the same rank as the gravitational force. It doesn't always work that way, but it does here. And momentum, that'd be magnitude of momentum. That would be ranked along with speed, because the mass of this object is the same. I assume they'd mean momentum of the orbiting object of the satellite. Kinetic energy, also related to speed, so it'd be the same rank. Potential energy would be the difference, the opposite of the kinetic energy one. So finally we have something different, because energy is conserved, because we're dealing with a conservative force, the force due to gravity. Potential energy would be opposite of the first four, so it'd be dCBA. Total energy, again, conservative force doing work. It is conservative, energy is conserved, so total energy would be the same for all of them. And then acceleration we've already addressed. And that's it for Think and